All right, so let's get started. I'd like to welcome you all to 6S191, Intro to Deep Learning. I'm Nick Locascio, one of the lead organizers, along with Harini Suresh, and I'll be giving the first lecture, introducing deep learning to you all. So 2016 was a pretty big year for deep learning, especially in the press. Wired kind of famously declared deep learning 2016 to be the year that deep learning took over the internet. We saw lots of articles, lots of press, and lots of hype around deep learning. And I want to get into why exactly people are excited about the potential and power of deep learning. And here's a little fun thing. We've reached such popularity that even celebrities are now getting in on the deep learning game. So recently, Kristen Stewart, for all you Twilight fans out there, authored a deep learning paper about neural style transfer. I recommend you check it out. It's actually pretty good. So people are excited about deep learning because it can solve a lot of AI tasks that are pretty difficult. So take, for instance, image classification. So given an image, we need to figure out what's in the image, and we want to produce a label. This is a very hard task that humans really take for granted. So there's the most popular image classification competition called ImageNet. And here's a graph of the error rates in 2010, 2011, 2012, and so on. 2012 was the first successful application of deep learning to image classification. So Chvetsky, Sutskever, Hinton produced a network called AlexNet that significantly reduced the error rates for image classification. And since then, we've seen even more and more dramatic decreases in the error rates, until actually now, deep learning solutions are even better than humans at this task. We've produced lower error rates with our deep learning models than humans are actually capable of this task. And we've seen similar gains as well in machine translation. So if you use Google Translate now, it is now powered by neural machine translation, which is a deep learning-based solution. And similarly, in speech recognition, I'm sure all of you on your phones have used this to maybe transcribe your text messages or your emails. And all of this is based on deep learning. And further in speech synthesis, and very excitingly in game playing. So there was a big result last year in which AlphaGo, a deep learning network, played against Lee Sedol, one of the top Go players in the world. And AlphaGo actually beat Lee Sedol. This represented a very big step in AI because people had thought Go was such a hard, complicated, large state space of a game that would take at least another 20 or 30 years for us to solve it and be past human performance. And we actually achieved that in 2016. And furthermore, there's been successes in things like playing Atari games with deep learning. So here is a superhuman deep learning Atari player that solves Atari pretty well. And there's many, many more of these things. So deep learning is a pretty breakthrough technology, and it can solve a lot of AI tasks. So we have a few goals for 6S191 to convey all of this to you. The first is we want to really teach you the fundamentals, the core concepts and algorithms that drive deep learning. The second is we want to give you practical skills to go ahead and implement neural networks in deep learning. So we have TensorFlow labs. You're going to learn how to use TensorFlow to do sentiment classification and tasks like that. The third is that we want to get you up to date on the current state of the field. So fundamentals are really great, but it's important to also know where the field is so we can figure out where the field is headed. And the fourth is we want to kind of create a community here. So we have coffee breaks, we have collaborative tutorials for you to work on. So talk with your classmates, make friends, and let's form a community here. So quick logistical things. This class meets 5 times this week from 10:30 to 1:30 p.m. There's one assignment for all of you that's taking this course for credit, and I'll get into that a little bit later. The typical schedule is that there's 2 lectures. There's lecture part 1 and lecture part 2, a short coffee break, and then time for tutorials. So about this assignment for those of you that are taking it for credit, you have 2 options to get credit for this course. The first is to come up with and present a novel deep learning research idea or application. And presentations for those are on Friday. The other option you have is to submit a 1-page review of a deep learning paper. So for option 1, we ask that you form groups of 3 or 4, and you present a novel deep learning research idea or an application. You have 1 slide and 1 minute to convey your idea to the class and the panel of staff and industry judges. And we have some list of example proposals on our website for you to check out. That'll be up tonight. The presentations are on Friday. We ask that you submit your groups by Wednesday, and you submit your slides by Thursday night, just as PDFs. There will be prizes for the proposals provided by our sponsors, and that can also be found on the website. The second option you have is to just write a one-page paper review of a deep learning paper. We have a list of papers on our website for suggestions, and you can look there for ideas on what to write about. And for class support, we have a Piazza, we have a website. All the lecture slides will be on our website, just at the /schedule. And you can email us anytime to ask us any questions or post on Piazza. We've got 6 great lectures lined up for you all. We've got a large supporting staff to help you through all of the tutorials and to help you through your assignment. And we've got 4 fantastic sponsors. So a big shout out to Google, NVIDIA, IBM Watson, and Amazon Alexa. Without them, we could not do the course in the way that we were doing it, and we could not provide all the things that we were providing for you. So a huge shout out to them. And one more thing about the sponsors. On Thursday, we've invited people from the sponsor companies to talk about how they're using deep learning in industry. So they're each going to give around a 25-minute talk on the applications and how deep learning is changing their industries and how they can build applications around them. So a big question that people ask about deep learning is why deep learning and why now? Neural networks have been around for quite a while, and it's only in the past few years that they've become so mainstream and so popular to solve certain tasks. And so the first question for why deep learning. Deep learning is powerful because it is able to learn powerful feature representations in an unsupervised manner. This is a difference from a lot of traditional machine learning techniques in which you have to handcraft features. So handcrafting features works in a lot of domains, but there's some domains kind of like image classification where you have very high dimensional data, and it makes it very difficult for us to craft features that are useful in prediction. So instead, deep learning takes the approach of taking in all of the data and figuring out what are the best features. So on the left, you can see a deep learning network has kind of learned edge detectors, it's kind of learned blob detectors, and it can form these together to form a face detector. And this is all done without us engineering these features. The second question, why now? So yeah, neural networks have been around for a while, but why is it only now that they're getting so powerful? So it really comes down to 3 things. The first is that there is the availability of large annotated data sets. So since we're learning these feature representations from scratch, we need a lot of data to really figure out what's important in the data. So the availability of things like ImageNet, which has millions of annotated photos, as well as online resources like Wikipedia for natural language processing tasks, has really driven a lot of deep learning progress. The second is advancements in GPU hardware. So we train our neural networks on GPU, and we usually get around 50 times speed up. So if your network takes around 2 days to train now, that means previously it would have to take around 100 days to train on just a normal CPU. So things that were previously impossible are now possible. And the third advancement is kind of just improved techniques in training neural networks and composing them. So let's just dive into kind of the fundamentals of deep learning and what kind of drives all of this. And at the core of every neural network is the perceptron. So the perceptron was invented in 1954 by Frank Rosenblatt, who was a psychologist, a neurobiologist, and an AI pioneer. He was really inspired by kind of neurobiology and the neuron and how it takes in inputs and can basically fire or not fire, make a decision based on the inputs. So a perceptron looks a little like this. And the output of a perceptron is dependent on the inputs, the weights. So we multiply the inputs by the weights. We take a sum of this. We add a bias term. And we apply some nonlinearity to this output. We can simplify this expression a bit by expressing it as a matrix multiplication of our inputs and our weights. And let's take a closer look at our activation function. What is it actually doing here? So here's an example of an activation function called the sigmoid activation. And at the core of every activation function is a nonlinearity. We're transforming our output from a linear feature to a nonlinear feature. The sigmoid also squashes our input between 0 and 1. There are many, many activation functions. The common ones that you'll see are things like sigmoid, tanh, and ReLU. And what they share is that they all have this idea of a nonlinearity. Nonlinearity is important because most of our data is nonlinear. So if we want to model our data and make decisions on our data, we need a nonlinear model to do so. So example A would be a simple linear classification. And we can draw a straight line to separate away the green from the blue. But in example B, we have nonlinear data, and we cannot draw a straight line through this to classify it. So we need a nonlinear function to fit it. So if we want to compute a forward pass of a perceptron, given some inputs and given some weights, we can do so just by multiplying out the inputs by the weights, taking the sum, adding our bias term, and then applying a nonlinearity. And in this case, our sum gets us 3.2. We apply our nonlinearity. That gets squashed down to 0.96. So how do we go about and actually build neural networks with perceptrons? Perceptrons are the base of every neural network. But we need to stack them, put them together in order to actually build these things. So we're going to simplify our perceptron diagram a little bit. There's a lot going on. There's a lot of arrows going on. So we can redraw it like this, which allows us to also produce multi-output perceptrons. So perceptrons that don't produce just one output, but multiple outputs. Furthermore, we can also produce multi-layer perceptrons. So a multi-layer perceptron has an input layer, a hidden layer, and an output layer. And this is a neural network at its most simple definition. You have an input layer, a hidden layer, and an output layer. And there's a lot of arrows here, so we're just going to redraw this as an X, so we don't have to keep redrawing all these arrows, because it gets a little tedious. So to extend an MLP, a multi-layer perceptron, to a deep neural network, all we do is just add more layers. We can add an arbitrary amount of hidden layers to achieve a deep neural network. So the next section is about applying neural networks. How do we actually use these to solve problems? How do we model a problem in order to fit kind of a neural network framework? So say I'm sitting in an airport, and I want to know if my flight is going to get delayed. And I remember on my way in, it was pretty cold. I think it might have been snowing, and my scarf flew off. It was pretty windy. So I have a pretty good idea that my flight's probably going to get canceled. But let's say I'm lazy, and I want to instead not think about this and build a model to predict if my flight is going to get canceled or not, because I don't like to do much thinking at the airport. So if I'm going to build a model, I want to give it the same information that I used to make this decision. Namely, let's say the temperature and the wind speed. And we want to see if our model can produce if my flight's going to get canceled based on these two features. So we can construct a feature vector from this. And we pass this in to a simple neural network that has two inputs, a hidden layer, and we want to produce an output. And our output is kind of just the probability that our flight is going to get canceled. We want to produce from 0 to 1. And this is why a sigmoid is really useful here, because it squashes any output we have between 0 and 1. So I feed these values into my network, and it predicts that my flight's going to get delayed with a 5% probability. And 30 minutes goes by, and my flight ends up getting delayed. So it was wrong. It was dead wrong. We haven't trained it yet. It doesn't really know how to fit this function. So it's important that we quantify how badly it's done for us to train it. So in quantifying loss, we look at the prediction of the model versus the actual label that we have for this. And we don't just care about one example. I'm a frequent flyer, so I care if my model can predict not just this flight, but the next 20 flights for me. So what we care really about is the total loss, how well it does for all of our examples. And we're going to express our total loss as a J of theta, is what it's called. So one way we could express this loss is something called binary cross-entropy loss. So we are only considering two classes. So in a probabilistic framework, we only want these two classes to exist. So we're going to penalize it pretty harshly when it gets the wrong decision. If instead we didn't want to predict if my flight would be canceled or not, but let's say we wanted to predict how long my flight would be delayed, how many minutes that would be. So this would be a regression problem. And instead, we would have our loss as just kind of a mean squared error. So there's many different loss functions depending on what our problem is. But we're just going to abstract this away into our j of theta term. So now that we have a j of theta, we've expressed our loss. And we want to actually train our neural networks to minimize this loss. So our objective here is to find the theta that minimizes the loss function. And our loss is just called this j of theta. And remember that theta is just the weights of our neural network, weight 1, weight 2, and so on and so forth. So I just want to reiterate this, that the loss is a function of our parameters. So as we modify weight 1 and weight 2, the loss of our network is going to change. And this forms kind of a function or a shape. And we want to find the minimum loss for, we want to find the parameters that minimize our loss. So we want to find the lowest point of this shape. So how do we actually go about minimizing loss? So let's say we just kind of start at a random point, and we know we want to get to the bottom. So what we can do is we can calculate the gradient at this point, which points in the direction of maximum ascent. But we want to go downhill. So we just multiply that by -1 and move in the opposite direction, downward. And then we form a new point based on that. So we update our parameters to get a new loss. And we can do this over and over and over again until we reach the minimum loss and we've reached convergence. This is called stochastic gradient descent. And kind of formally, the algorithm for this might be that we loop through all of our training examples. We compute the loss for each of our training examples. And we want to update our parameters with something called the update rule. So the update rule is just we're forming new parameters based upon the old ones. But we subtract an eta times our gradient. So let's focus on this part right here, our dj, d theta. How do we go about and actually calculate this gradient? Because it's really important that we find the right direction to move in. So let's say we have a simple neural network that just has 3 nodes. It's got an input node, a hidden node, and an output node. And let's look specifically at weight 2. So we want to see how weight 2 changes the way our loss changes. So we want to calculate dj, d weight 2. In order to do this, we apply the chain rule to dj, dw to get dj, do times do, d weight 2. The chain rule is a pretty general concept that we can apply to any of our weights. So we can also look at weight 1 and see how the gradient changes with respect to weight 1. So the gradient relies on dj, do, as well as do, dh. However, do, dh is not a constant. Do, dh depends on weight 1. So we apply the chain rule yet again to get our third term. And this is what's kind of meant by the idea of backpropagating gradients, because oftentimes the gradient of one parameter depends on a previous parameter. So there's a long chain of these, and that's kind of the idea of backpropagation of gradients. All these slides are online, so I just want to get some of the general concepts across to you, but feel free to write down the math as well. But these are all online on our website as well. So now we have a good idea on how to calculate a gradient, how to move in the right direction, and how to minimize our loss using this. However, there's some kind of tricks and tips that are really important when we're training neural networks. So I just want to kind of briefly cover some of these. Because in reality, our loss function a lot of times may be hard to optimize. There may be really high peaks, really low troughs, and it might be hard to find the actual minimum. So let's take a closer look at our update rule, that we're updating our theta based on our gradients, which we talked about how we calculate, but also this eta term. So eta is also called learning rate, and it represents the step size, how large of a step that we're going to take with each of our gradient updates. So it's important that we choose the right learning rate, because say we choose a very small learning rate, we're going to take a lot of very tiny steps, and it's going to take us a really long time to reach our minimum. So this is bad because it takes a while. But secondly, it also might prevent us from actually finding the global minimum. So with a very small step size, it's very easy to get stuck in this kind of local minimum you see on the right. And we never actually reach the global minimum on the left. Secondly, say we choose a learning rate that ends up being too large. Yeah, go for it.
Is there any
Yes, so the way you define your network based on your, basically neural networks are continuous functions that are always differentiable. But I guess lecture 4, you'll see some things in reinforcement learning that may not be differentiable. And there are ways to deal with that by kind of sampling the gradient. But for now, we're considering all networks that are completely continuous and always differentiable. So we can always kind of find this gradient. So we've covered a small learning rate, but also there's the issue of a large learning rate. So with a large learning rate, we have our error gradient, but we kind of just bounce around a whole lot, and we never actually reach convergence. And it's actually even possible to reach divergence and increase the loss by kind of just bouncing upward. So large learning rates are bad, and small learning rates are bad. We want kind of that Goldilocks in the middle. What is a good learning rate? So there are a couple ways that we could go about and try to do this. The first is to kind of just guess. Try a whole bunch of different values and see what gives us the best result. This is pretty time-consuming and may not be the best use of our resources. So instead, we're going to do something smarter. And that something smarter is called adaptive learning rate. So we're going to throw away this notion of a fixed learning rate entirely. And we're going to consider learning rates that can adapt and change based on how the learning is going. And we can adapt and change this learning rate based on a whole variety of parameters. So we could change on how quickly the learning is happening, how large the gradients are, how large our weights are. We can even have different learning rates for different parameters. So there are a bunch of different adaptive learning rate algorithms. There's things like ATOM and Momentum and NAG and Adigrad. And they each deal with this problem in a different way. But at the core of all of them is some smarter way to change the learning rate based on how the gradients look. So here is an example showing kind of a comparison of learning with different learning rate optimization strategies. So in red, you'll see stochastic gradient descent. You can point at this here. So in red, you see SGD. And it's really kind of getting stuck. So this is in a saddle point. Saddle points are pretty hard to optimize because the gradient is pretty much 0. So it's very hard to find the right direction to go in, and our gradient values are very small. So with a fixed learning rate, we can really get stuck in a saddle point. However, if you look at the other learning rates, the adaptive learning rates, they can recognize that we're in a saddle point and escape pretty quickly by increasing the learning rates. So I think the best one here is the yellow. At a delta escapes pretty quickly. Similarly, with other types of saddle points, we see similar results in that SGD can often get stuck with this fixed learning rate, and doing something smarter with an adaptive learning rate gets us faster convergence. So the second part of training neural networks in practice I want to talk about is this idea of mini-batches. So we've talked about stochastic gradient descent so far. And we haven't really talked about the stochastic part and why it's called stochastic. So it's called stochastic gradient descent because I kind of lied to you. So when I say I take this dj d theta term, which represents the gradient, we actually only calculate an estimate of the gradient. To calculate the entire gradient, we would have to go over our entire data set and compute the loss for each of them. This takes a really long time. So in stochastic gradient descent, we just look at one example at a time, compute our gradients, and update our parameters based on that. The issue with this is that we're only looking at one example to get each gradient. So this is a pretty non-consistent and kind of stochastic representation of our loss and of our gradient. This can present a lot of issues because it's not a very reliable and consistent learning signal. So instead what we can do is we kind of batch our inputs. So instead of just taking one input at a time and computing a gradient based on that, we get a whole batch, say around 32 examples. And we compute the gradients for each of these, we sum them up, and we have a more accurate estimation of what the gradient actually is. And then we can apply this more accurate estimation of the gradient to our update function and achieve the same loss minimization that we had seen earlier. So mini-batches have a few advantages. So the first I've talked about is that it's a more accurate estimation of the gradient. So this leads to kind of smoother convergence, better convergence, and we have a more accurate representation of what the loss looks like. The second advantage is that mini-batches can lead to faster computation. We can parallelize a lot of the computation in a mini-batch because when we're calculating each of the gradients, our model stays fixed. So we can parallelize our fixed model across many processes or cores or what have you. And we can compute each gradient within a mini-batch at the same time, accumulate these, and then apply them in the update rule. Whereas previously, in stochastic gradient descent, we would have to compute the loss for one, update our rules, compute the loss for another, update the rules. So batching our gradient calculations together actually leads to faster performance and faster training. The third bit I want to talk about training neural networks is how do we fight overfitting? So neural networks are really powerful models that are capable of learning all sorts of kind of features and functions. But sometimes they can be a little bit too powerful. And they can either overfit or maybe memorize training examples. And this is a big problem. So this would be an example of overfitting. We have some blue and some red. And we want to find a function that kind of gets the gist of it. So in the middle, we found a pretty good function. On the right, we've really overfit to this data set because we're considering things that may not be important, and we're kind of drawing this very unnatural shape, which is not the best solution. And it doesn't generalize outside of the training set. So the big idea with overfitting is that we may do really well on the training set, but when it comes to real-world examples, we've learned something that's so specific to our training set that it doesn't apply outside in the real world or in a test set. So there are a few different techniques to do this. We all kind of say that under one word, regularization. Regularization is how we prevent overfitting in machine learning and in neural networks as well. There are a few techniques I just want to go through on regularizing neural networks to kind of prevent this overfitting. The first is called dropout. So say we have a normal neural network, deep neural network, as we had seen before. And with dropout, essentially what we do is we take some random nodes and we drop them out. We remove them from the network. And we compute our loss, and we do gradient updates with this kind of dropped out network. And then we drop out a different set of nodes. And then we train on this and compute our gradients and updates. And essentially what we're doing here is we're making each of our nodes not very reliable. And we want our network to not rely too much on any one node. So by making kind of this distributed decision, we are naturally kind of regularizing our neural network to kind of be a committee of actions and not just the decision of any one node or any one classifier. So that's kind of why dropout works from an intuitive standpoint. There's also a lot of math detail standpoint that you can look into after the course as well. The second technique for regularization is a pretty simple one, and it's called early stopping. So say we're training a neural network, and the core idea here is we don't want to give it time to overfit. Neural networks are very powerful. If we give it enough time, it's going to do really well on the training set and maybe very poorly on a test set. So it's common when we're training to have a training set and, say, a validation set. We only train on the training set. The validation is really just for testing and to give us kind of a pulse on how good our model is. So as we're training, with each epoch, it's often common to see the training accuracy go up, the validation accuracy go up, and continue, the training accuracy goes up, and the validation accuracy goes up, until you reach a point at which the training accuracy goes up, but the validation actually goes down. And it continues to go down, and it continues to go down and get worse and worse and worse. So you train this for 2 days, and you end up with the model at the end. And it does actually really poorly on your real-world task. But we had a model earlier on that did pretty well. So early stopping, essentially, you just kind of keep track of how well the validation is doing. And you just kind of stop the training once it starts doing worse. It's a really simple technique, and it works really well in practice. And the core idea is we just don't want to give it the time to overfit to our training set. And here's kind of just like a graphical representation of this. You can see the training set accuracy continue to increase. Our validation accuracy increases, but eventually kind of tops out and starts to get worse and worse and worse. So we want to stop it before it gets worse. The third regularization strategy I want to talk about is something called weight regularization. With weight regularization, it's common in machine learning that large weights in our models kind of lead to overfit models. We're making really large decisions on small features, so this is typically not the best way to go about this. So what we want to do is we want to enforce our model to have tiny weights. And the way we can do this, so let's recall our objective here was to minimize our loss function with respect to our parameters. So we can just add an additional term called a regularization term. And basically what this is we sum up the magnitude of all of our weights, and we add this to our loss function. So if we have large weights, our loss function is going to get larger. So in this way, we're kind of optimizing these two different tasks. The first is our first loss, which kind of just calculates how well we're doing on a task. The second part of this loss function is how large our models are, how large our parameters are. So with this dual task, we're kind of fighting between fitting the training data really well, but also keeping our model weights small. And in doing so, you kind of achieve a balance between strong models and models that can fit the data. And all this together would form our J of theta, and we could apply all that we've learned about stochastic gradient descent to find the minimum. Yeah? Yeah, sure. So I think it kind of relates a little bit to the example we saw in Dropout in that, oh yeah, sure. The question was, why do large weights lead to overfitting? And so I think the intuition behind this kind of relates a little bit to Dropout as well. If we rely on any one node to produce our decision, like a single node can learn a strong classifier that may not fit to all the examples. So I think we have this assumption that our data is going to be complex and difficult to model. So it's going to take a committee of many different classifiers to make this decision. If we have simple enough data, then yeah, large parameter weights work really well to fit that. But I think deep learning really succeeds in these modalities where we have very complex data that cannot be decided by a single factor. So I think you could say that like a small network that computes a very simple function can fit a lot of simple data. But when you have complex data, a small network cannot fit that. And it can maybe overfit it by producing a simple rule, but it can't fit it well. So we kind of want to utilize the fact that we have many parameters so we can fit complex functions. So I think that's kind of an intuition on why large model weights could typically lead to overfitting. We want to rely and use the entire power of the network to do so. Yeah, also, other questions? Yeah, please, yeah. Yeah, so this is an L2 norm. The question was, are L1's norms ever used? I believe so. L2 is typically more common. So for L1 norm, you just wouldn't square it. You would just take the value of it. And I think L2 norm is used a lot because I guess it's kind of just like a very traditional machine learning technique. I guess I'll point out one other thing as well. There's this lambda here, which is our regularization parameter. So we can kind of tune how much we want to penalize the large weights. With a large lambda, we penalize it more. With a small lambda, we penalize it less. And we can kind of tune this based on how well our model is doing on our validation set. So yeah, just want to kind of do a recap of some of the core fundamentals that we've covered. The first is, we've gone over the Perceptron classifier, what it is, how it works. We've kind of covered how to stack perceptrons to form neural networks. We've shown how to formulate problems within a neural network framework. We've shown how to train neural networks to perform certain tasks. And lastly, train neural networks with backpropagation and stochastic gradient descent. And lastly, we've gone over a few kind of techniques and tips for improving the training of neural networks. So that concludes lecture 1, part 1. Harini will be giving lecture part 2, in which she will discuss how do we model sequences of data. So we've only really dealt with fixed representations, but if we have something like a sentence, Harini is going to explain how do we deal with that in a neural network framework. So thank you. And any questions?